What can you get for $1? What if I told you that you could get a complete field testing framework for any digital IC, probing it while it's out in the wild, experiencing real conditions? What if I told you that hardware in the loop can be easy? That when you've made a digital design, you can take those simulation tests you created during development and turn them into live hardware probes, reusing them as is against actual devices. That you could write tests once and use everywhere, through the desktop or even on a microcontroller. That you could easily extract VCD waveforms out of physical chips in circuit, FPGAs, ASICs, anything really. What if I told you that that line was never actually in the movie? Hello! Let me show you my path to live hardware verification made simple. Multiple ways to break out of the matrix and take a digital design simulator test bench and put hardware in the loop running those same tests but against real-world chips. Now watch out, you may fall in love with this approach because I sure did. Have a look at why. I did testing while creating my ASIC projects running in pure simulation. Now I have the ASIC in hand, so here's the same set of tests, but running straight on the tiny RP2040 and talking to the chip live, doing everything directly on these demo boards, no computer required. Cool. Also, my project works, so that's good. And here, same tests, but running on desktop and controlling the device through an external FPGA. Or hey, why not everything on a Raspberry Pi 5 connected to the ASIC? I did a stand-up job with the wiring there, but still, wow, look at it go. It works, and in these cases, we even get waveform dumps to pour over. Now, the VCD files can tell you exactly what's happening at every step. That's really helpful when you don't know what's going wrong. So, unlike with SIM, however, you can only get signals from exposed I/O this way, right? But wait, there's more. We can even get the best of both worlds. A circuit interacting with physical hardware, but still be able to peek at the deep internal state by running tests on the desktop while the actual design is inside an FPGA. So here the tests are being driven by the desktop but going through the FPGA, which has a design talking to an actual SPI flash, but also has the ability to let the desktop remote control and inspect the internals, all over USB in this case. This way, we can get detailed information about what's going on inside the design while still interacting with external hardware. That's pretty wow.
Wow.
So that's the same set of tests with no changes running in all those scenarios. Okay, really cool. But why would you need 50 ways to run the same tests? Well, you don't. Now, the same tests and library I'll show drive all of these cases, so which way you use depends on what you have and what you care about. Engineering's all about trade-offs, so you may care about speed or more about the device being out in the field there, operating under real conditions. Some methods require having access to the design source, others don't, so you can probe chips in the world, anything you want. Some are just easier to set up. Now, I'm going to be covering 3 scenarios. We're going to be running tests on a computer with the device circuit at black box outside in the world, running everything directly on an MCU that's wired up to the target device, and running tests on a computer while the circuit is inside an FPGA that can control and probe it deeply, but all while letting the design be connected to external components. The great thing is, this is actually pretty easy. Well, it is now that I've gone through the gauntlet anyway. So welcome back to my lab. I'm glad you're here. Now get comfortable and strap in, because we're going to do all of these. What you're going to need if you want to play along is a DUT, a device under test to look at. Now this can be a design of your own, an ASIC, or any digital chip in the world, so flash memory, a sensor, whatever. Second, a framework that can run tests on a DUT. Third, a representation of the physical device that the framework can use that will actually play with the real pins and report back real values. And finally, a set of tests that you want to perform, or just things that you want to look into. The device and tests are up to you. The other half I'll give to you for free, which is a good thing because they're the annoying bits. Now let's begin with that framework. This all started because Tiny Tapeout, an educational project that lets anyone get their own designs onto an ASIC, encourages people to write test benches as they dev, and I thought, wouldn't it be great if our users could, once the chips are finally in hand, just run those same tests on the ASIC itself? Now, if you know my work, you know that I can fall down some crazy rabbit holes if it's interesting or might lead to something useful. And that's sure what happened here. So, though the designs can be written in Verilog, we use cocotb for testing. If you don't know it, don't worry, it's Python, and look at this. You can tell just by looking at this that it's starting some process, then checking the device says it's busy, waiting for that signal to go low, and then checking the device says it's ready. So it's really easy to get started. cocotb makes it simple to write test code, and it's running Python, so it's a breeze to do all the wonderful things you want. Read stimuli from a file, check against a golden model in MATLAB, do randomization or data analysis, include in your CI, just a bunch of stuff. Now, if you want a softer introduction, or if you know cocotb but would like to up your game and make the most of it. I'm preparing some content and a workshop on that, so check the link in the description if you want me to let you know when that's available. The way cocotb works is by doing your testing in Python, but running the design in an external simulator. Now, cocotb is called that way because it's a coroutine-based co-simulation test bench. But we don't want a simulator. We want the real deal. And when I looked into it, it wasn't a simple affair to get hardware in the loop. So, to cut to the chase, I took the cocotb version 2 way of doing things, dropped the co-simulator, and created Microcotb, a cocotb v2 compatible system that runs on microcontrollers or anything you can get micro or full Python going on. A Microcotb is open source and has examples for all the things we're doing today. Though it can't know your specific design or device, it makes it really easy to set up a DOT for any interface. Now that's the only place you'll have to spend any time getting up and running, and on a Raspberry Pi, it's as little as like 3 lines of code. Now to prove it, we're going to get up and running right here, right now. I'll start by going over how you make a Raspberry Pi look like any DUT, and along the way, show you a really easy way to use the GPIO on a Pi 5 that deals with all the libgpiod stuff, just as a side bonus. So let's do it. I've got the Raspberry Pi 5 back there, pretty horribly wired up to all the I/O of the ASIC that's sitting on the demo board, including the clock and reset. And the RP2 on the demo board is just sitting there, also tied to all the lines, so we can use it to passively snoop on what the ASIC sees and does. Now both of those are over there and I'm over here. So I'm connected to them in these windows. This is the Pi 5 in one window, and I'm also on the Pico on the demo board in the other through the laptop and then the USB serial. On the Pi 5, let's start by creating a virtual env, and once that's activated, from there we can install Microcotb using pip, easy peasy. For this we also need GPIOD. Now let's go start up Python. Now normally I'd put all we're going to be doing in a subclass, but I'll do it live just to show how easy it is. Now I have it wired up in some particular way. Check out the beautiful notes I made while doing this. So in my pins here, I just have the list of GPIO numbers. I don't want to have to retype all that, so it's in there. Okay, Python. Now first off, import that list of pins. Okay, they're in here. So now we want to create a DUT that can use these pins for various things. I'm basically going to type 5 lines of code here, but I want to walk through it slowly to show you some stuff along the way. First off, we need to import the library. This is for the Pi 5, so that stuff is outside the Microcotb core, and we import it from Microcotb RPI. So now I need to create this DUT. So it's just a dumb base class. It doesn't know anything about our setup. Let's change that. I can add I/O to it by giving it a name, a direction, and a list of pins. So let's start with settings. This is going to be a byte, these 8 GPIO pins, and we're setting them up as outputs. Now they're coming into the ASIC, going out from the Pi 5, so direction here is output. So I can see and set its value the cocotb way, but it also has a superset of features so you can do less annoying stuff that feels natural to me, because life is short. On the ASIC side, these are the UI pins, and look at that. They're reflecting what we're doing on the Pi side. So it works, and really, that's all there is to getting a DUT. But let me show you a few other things. Now, here's the thing that can be weird if you're not a Verilog guy. This is all set up like Verilog, or like datasheets. Index 7 is the most significant bit. So look at what's changing. Now that's how it is in cocotb Testbenches, so that's how it is here. An addition I've proposed to cocotb with mitigated success is to have working slices. They were only lukewarm on that, but I find it really useful and natural, so Microcotb has a superset of functions that can also use slices like this. So note that this is like an HDL. 6:4, that's bits 6, 5, and 4 inclusive there, so it's 3 bits wide. So this design on the ASIC has 2 modes, loopback and counter, that are controlled by the LSB of this settings thing. So that's bit 0. We would be using that a bunch, so we can give it a name. We can add aliasing to bits and slices with some convenience methods. Add bit attribute takes a name, the source port, and the bit in question. And now we have a mode attribute which acts like just a standard signal. We can get and set stuff live like this or during tests that will affect the relevant bit. So that's cool and pretty handy. If we were doing tests, we'd also set up some I/O for the 7-segment display output from the ASIC. So that would be something that we look at from here. Set it up with a direction of input this time. So this is an input, so it's read-only. And finally, we can have the bidirectional pins. For this one, we want to choose if it's a pin that's an input or an output on the fly, nice and easy. So let's call it bidir and set the direction for this guy to configurable. A configurable I/O like this gets the usual attribute added, but it also gets an output enable, by default called whatever underscore OE. And setting any of those bits to 1 will enable output on that line, so you can write to it. Okay, we have our 3 ports, but this thing has also got a not reset line and a clock, so we'll add those as well. And they're just the same as all the rest, except they're only 1 bit wide. Alright, we now have a complete reflection of our DUT, and we can play with it to our heart's content. I'll also bring the mode bit high to put it in counter mode. Now, if we look at the display, it has some value. And if I toggle that clock line a few times, it should count up. So this isn't cocotb, but I've added a few helpers like invert and clock to these signals. So clock inverts twice. Now, the display went up. So let's do that another bunch of times. I'll give it a parameter this time, and we can see it working. Now, the test bench in the examples uses the names from Tiny Tapeout, so UI in, UI out, and such. But you can see this file is really short. Creating a runner to run the test and saying we want VCD output and temp. The tests are the same we use on every platform, so they're in this distinct module here, testing the loopback, counter, other stuff. Okay, we run this. That was quick. The VCDs are now in temp, and we can take a peek. So there are the Tiny Tapeout signal names, and they're doing their thing. Okay, that works, but it's too simple of an example to be too interesting. So look at this. This is the test bench I created for the SHA-256 encoder I made. It's got lots of tests, but the thing to notice is that it's playing with a bunch of named signals like data byte in, result next, stuff like that. Now, the Verilog test bench is making these nice names by assigning them as appropriate from Tiny Tapeout generic names here. To get these tests running with hardware in the loop on the Raspberry, I derived a class from the base DUT and did those add bit attribute aliases there. And the actual run is just boilerplate of create the DUT, say if you want VCDs, and go run the test. Now to run that, let's get the project loaded on the ASIC. So we select the project from this shuttle. There it is. Then just launch that from the Raspberry Pi side. Now it's going to whoosh through and feed in strings to hash and check the results, and that's what it's doing. Now it's trying a bunch of things. It also does boundary tests on various block sizes, and it all looks good in about like 16 seconds. We've done a whole bunch of tests, and now we can look at what would happen. So let's copy that file over and open up GTK Wave. Wow. So in yellow is the test feeding in the input. So a start pulse up top, then it's clocking all those bytes of data. Once that's clocked in, the design says it's busy, so we wait. Finally, the last bit, some zero padding. At some point, it says it's ready, and we can clock out the hash values, and that's what these guys are. And really, that's how easy it is to get your tests running against real hardware. Now that system is crazy useful. It works on the Pi, it also works on the RP2. Now the amount of power the Pico give you for about $1 is nuts. Well, $1 if you're getting the bare RP2 chip like I did for the demo boards. If your time isn't actually free and you just want to drop in a Pico rather than do more PCB layout, you can do that for a few bucks. The result is the same. All the tests run as is on the RP2040, though admittedly a hell of a lot slower. There's a limit to what you get for a buck, I guess. But the upside is that you get complete freedom. This runs without an external computer, so the whole sequence can be embedded absolutely anywhere in the real environment. Now you can check the examples from the Tiny Tapeout SDK for details. The main difference with running on the Pi 5, for example, is that when you're setting up the DUT, I wanted an efficient system. So rather than passing a bunch of pins to check individually, you give it read and write functions that lets us use this ugly but low-level machine stuff. That is a big improvement over reading a pin at a time in terms of speed. All that's online too, so links in the description, blah, 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 blah. Now, all these Raspberries are cool, but they're just examples. If you wanted to use some monster FPGA with fast COM bus, this framework would work with that too. to pretty easily. Now, I'll actually show an example through an FPGA, just like we did with the Pi there. But first, the thing to note is that in one case on the Raspberry Pi, we got speed and waveform dumps to look at. Okay, in the other, on the RP2040, you're computer free. You could send the whole thing out to the North Pole and test the device hourly, logging results or whatever you want. All of these, however, are black boxes. You can only see the external I/O pins. Now, whatever's happening inside the design remains a mystery. So what if you're trying to debug some interaction with other real hardware, but you also want to look deep into the design? For this, we're going to bust out an FPGA, and I'll show you how to do that. Now, it could be any FPGA, but these boards are great for a few reasons. This is the Anything PMod, a board I'm going to talk about extensively in my next video, and which will be released as open hardware and made available, so stay tuned for that. Now, they're pretty cool. They have peripheral and controller side PMod headers, USB bootloader, a good deal of I/O. They're pretty nice. So in this next example, the main reason to use them is just that they're easy to talk to over USB. So let's look at that. Okay, first a really simple example. Here's the test bench I did for the Neptune guitar tuner. It's got the tests and a tb.v verilog file that does the thing where I'm giving nicer names to generic signals. So I took all this stuff, the tb.v and the original verilog design, and made one change. I added a 3-bit disk state output, and then here at the bottom, I'm just assigning it to some deep internal value, from the top down through tuner, then discriminator, to assign it to its current state and reflect that out into the world. So that's the change I did to the test bench to go look deep. Now, the higher con keep comment in there, well, that's a Yosis way of ensuring the signal name isn't munged when the verilog is processed. Now, with those two files in hand, we can go into my subsystem. This is the simple USB bridge, a dumb protocol I made to be able to talk over USB serial and control the DUT. It's simple and not so fast, but I did it over a weekend to make this demo and prove the point. There are way better and faster ways, but you know, it does the job. Now, the sub support on the FPGA side is all in Amaranth, so the only thing I have to do is make a module with the same interface as the tb.v there and tie it to the external verilog with an instance thing here. Derive a class from this test bench. So the test bench is the parent, and in the init, I specify the signals to expose and which direction they're going, i.e. is it going out to the DUT or coming in from the DUT. There's a lot more behind the scenes. Let me know if you want to hear more about that. But for you, customizing some design, that would be it. Now, when this is built, I can put the FPGA board into DFU mode and then send over the bit stream. And now there's something to connect to over serial. Now, it's a protocol that's meant to be a bit efficient, so it's not pretty to use straight from a terminal. Still, it's there. And if we come into Python instead and import the basic sub.dut class and just create one, well, it's just not too interesting. But it understands how to ask the FPGA for the available signals, and they know their width and everything. And you can look at that. It's pretty neat. It's all auto magic. Cool. So if we run the tests, it'll go through there and just do its thing. And there we passed. Okay, so here's the interesting bit. If we look at the resulting VCD of running on this FPGA, you can see that in this test you have a bunch of info, but down at the bottom, what's that? That is the deep internal state of the discriminator submodule. And though we're running on physical hardware, we can still see the state machine transition and do its thing and just as the process goes along, you know? Now that opens up a whole lot of possibilities. So for a final example of this, we're going to look at something more interesting and a lot deeper. Now this thing is now running what I call the SIM file reader. It's got files on the SPI flash that's attached here, and in the design there's a SPI master connected to that, a flash reader on top of that, a flash FIFO that uses the reader to provide a FIFO buffer and just, you know, so that the flash just looks like a big long string of bytes, and a file parser that takes that stream of bytes and interprets it as a set of register settings, in this case for a sound generator chip. Now that's a lot of layers. You could connect a logic analyzer to the SPI flash and see that without issue, but how are things going in all the intermediate layers there? Let's find out. So this is the same setup as before, but the wrapper has many more signals. Some are from the top, some are from the FIFO, one is from the flash reader, and you go all the way down to the SPI. So I wired it all up in the combinatorial domain here, and then declare the direction for all the signals like we did before. Cool. Now, if run this test, it just works the same, and it does its testing. It discovers the signals, starts the testing. Looks good. Okay. Fast forward. Okay, check out the VCD file. That's a lot of data. Now, if I was having a problem, I wouldn't want to start at the SPI layer. That's just a bunch of bits. So let's do sanity checks all the way up. Now, first thing I can see is that just after enable comes in here, the flash reader triggers a pulse. And here we go, the SPI transactions begin, and so that's a really good sign. Up above that, you can see the FIFO stuff in green. As SPI data starts coming in, the buffer begins to fill, and you can see here's the R level, the level of the buffer. It goes up and up and up and up, and at some point it starts going down. Okay, so the SPI is producing data, it's filling that buffer, and then at some point, someone above is consuming it, so the level goes down and down and down. Now, this pattern looks good. When the buffer's empty, the ready goes low, some SPI, ready, 4 bytes get munched on, then more SPI, ready. That's decent behavior. Okay, so how's the actual data look? In the FIFO, it starts with stuff in the 50s there. Now, if you switch this to ASCII, you can see sim1, that's the magic bytes from the file. So the FIFO is starting to look okay. You could check this against the original file and see that it matches. I can tell you it matches now. Okay, up the chain. So registers come in batches. The very first fresh batch has 16 settings. That makes sense because the file is initializing all the registers and they're all 0 except one of them. Then the subsequent batches have 4, 3, 1 repeated a few times, and 2. That, not coincidentally, matches what we were hoping to find, which is why the tests pass. So in this case, everything is working smashingly, but you can see how useful having all this visibility would be when debugging, even though we're doing it with like real hardware in the loop, even though we're talking to real flash. The really cool thing with this approach is that you can choose which parts of the system are real hardware and which you need to be able to inspect deeply. You could tie in real sensors, add flash, have some external system modeled in Python controlling the design through the bridge. It's whatever you need. It's mix and match. Now, the only real downsides of this method are that you have to reconfigure the FPGA for every combination that you're interested in doing, and you need some layer to bridge over the computer. So, I mean, I made the sub thing, but it's simple and slowish. Still, you can use it, so there's that, but everything else would have to be figured out. So for anyone who wants to play with all this, I'll put everything online as soon as possible when I put out the video about the little boards, which will also be available as open hardware, like I said. So speaking of these dev boards, the other reason I'm using them is that they're great for this final scenario, using a pure FPGA bridge to test anything, which I'll call FPGA I/O, say. This is a lot like the first cases in that whatever you're testing is completely external to the FPGA, so it can be any chip you want. But here, I want to connect to a TT Demoboard, and since it has host PMODs, and this guy has peripheral PMODs, it simplifies wiring a lot, especially compared to the Pi 5 there. So look, I'm going to use these two PMODs for BIDIR and output from the ASIC, and pipe the controller PMOD to the inputs. Also, wire up the clock and reset there. That's that jumper. So with that, rather than run on the FPGA, I'm just running tests through it, like we did with the Raspberry Pi. The advantage here isn't so great because my sub sucks, but it still shows that you can, of course, go through FPGAs, not just Raspberry Pis, and with this method, only a single firmware for the FPGA is ever needed. It just needs to know how to respond to Testbench, and it'll work with anything you can wire to it. Do this with a powerful beast over Ethernet or PCI Express or whatever, and you've got some crazy potential for hardcore testing. Now, throughout all this, I talked a bit about the tests themselves, but I was really focused on the getting hardware into the mix part of it. There's a whole lot to cover about testing itself and about cocotb in particular. I am right now preparing a deeper dive focused on that side of things. Now, if you're interested in that, and actually even if you're not interested, do me a solid. I'm trying to figure out how much juice to put into it and where. So it would really help me out if you'd click on the link at the top of the description up there and answer really any of the questions in the form. As always, it's been a pleasure sharing this with you. I hope you found it of use. May your clock cycle and all your latches latch. Take care. We'll see you soon.